Right now, as you read these words, something invisible is pinning you in place. It dictates whether your coffee stays in your cup or floats away. It determines whether Earth's atmosphere clings to the planet or dissipates into the void. It choreographs the cosmic ballet of galaxies across distances so vast that light takes eons to traverse them. You've lived with this force every moment of your existence. You think you understand it, you've been taught about it since childhood. Drop something, it falls down. Simple, obvious, gravity pulls things toward Earth's center. But here's what's going to fundamentally reshape your understanding of reality. What you think is pulling you down isn't pulling you at all. What we call gravity isn't even a force in any conventional sense. It's something far more bizarre, a warping in the very structure of existence itself. Before we unravel this cosmic mystery, if you're ready to have your perception of reality fundamentally altered, hit that subscribe button and drop a comment. Have you ever questioned why things fall? Because tonight, everything you thought you knew is about to change. Consider your current experience. You're sitting or standing somewhere, you feel weight pressing down. If you're seated, the chair pushes up against you. If standing, the floor resists your feet. Every sensation tells you the same story. Something is pulling you downward toward Earth's center. This narrative feels so self-evident that questioning it seems absurd. It's like questioning whether the sun rises in the east or whether water flows downhill. These are observable facts, experienced daily, confirmed by every interaction with the physical world. Except the story is wrong. Completely, fundamentally wrong. It's similar to how ancient civilizations believed the sun orbited Earth, because that's what they observed each morning. The observation was accurate, the interpretation was catastrophically mistaken. They were observing reality through a framework that concealed deeper truth. You're making the same mistake right now, not because you're ignorant, but because your brain evolved to survive on Earth's surface, not to intuitively grasp relativistic physics operating on cosmic scales. The truth about gravity is so counterintuitive, so alien to everyday experience, that even after you understand it intellectually, your senses will continue reporting the old, incorrect interpretation. Your brain will keep insisting something is pulling you down even when you know better. This disconnect between perception and reality reveals something profound about the universe. It doesn't operate according to human intuition. The cosmos follows rules so strange that our evolved cognitive machinery actively misleads us about basic physical facts. For centuries, humanity developed increasingly sophisticated mathematics to predict gravitational effects with extraordinary precision. These equations worked brilliantly. They predicted planetary orbits, explained ocean tides, enabled the discovery of unknown planets through pure calculation. But working and understanding are different things. You can predict something's behavior without comprehending why it behaves that way. The equations were correct. The conceptual framework underlying them was incomplete. Drop a like if you're ready to discover what gravity actually is, because the answer is going to sound like science fiction, except it's been proven true in countless experiments. Tonight, we're going on a journey from comfortable misconceptions to uncomfortable truth. We'll trace humanity's evolving understanding of gravity, from ancient philosophy through Newtonian mechanics to Einstein's revolution. We'll discover why the weakest force in nature dominates the cosmos. And we'll confront the unsettling reality that you've never felt gravity in your entire life. In 1687, Isaac Newton published Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy. This work revolutionized human understanding of motion and force, establishing principles that would dominate physics for over 2 centuries. Before Newton, explanations for why objects fell were largely speculative. Ancient Greek philosopher Aristotle claimed heavier objects fell faster than lighter ones, a hypothesis easily disproven by observation but accepted for nearly 2 millennia. Medieval scholars proposed increasingly elaborate mechanisms involving crystalline spheres and divine intervention to explain celestial motions. Newton changed everything by demonstrating that identical mathematical principles govern both terrestrial and celestial mechanics. The same force making an apple fall from a tree also kept the moon orbiting Earth and Earth orbiting the Sunday. This unification was revolutionary because conventional wisdom held that heavenly bodies operated under fundamentally different rules than earthly matter. Newton's law of universal gravitation stated that every mass in the universe attracts every other mass, with a force proportional to the product of their masses and inversely proportional to the square of the distance separating them. Mathematically, F equals gm1 m2 divided by r squared, where g is the gravitational constant, m1 and m2 are the masses, and r is the distance between their centers. This elegant equation explained countless phenomena. It predicted planetary positions centuries in advance with remarkable accuracy. It explained why ocean tides rose and fell, the moon's gravitational influence pulling on Earth's water. It revealed why planets farther from the sun moved more slowly in their orbits. The inverse square relationship meant gravitational force weakened rapidly with distance. Newton's equations transformed astronomy from descriptive observation into predictive science. For the first time, humans could calculate where celestial objects would be in the distant future, with precision that seemed almost magical. Comment below, did you know Newton's equations are still used today for most space navigation? Despite Einstein's later revolution, Newtonian mechanics remains incredibly practical. Let me know your thoughts. The law's predictive power seemed to confirm its fundamental correctness. When astronomers noticed irregularities in Uranus's orbit after its 1781 discovery, they didn't question Newton's equations. Instead, they assumed an unknown planet must exist, perturbing Uranus gravitationally. In 1846, French mathematician Urbain Le Verrier calculated where this hypothetical planet should be based purely on mathematical analysis of Uranus's orbital deviations. German astronomer Johann Gaia pointed his telescope at the predicted coordinates and discovered Neptune almost exactly where Le Verrier's calculations placed it. A planet discovered through mathematics before any human eye observed it. This triumph cemented Newton's reputation. If his equations could predict invisible planets billions of kilometers away based solely on tiny orbital perturbations, surely they represented final truth about gravity's nature. But Neptune's discovery created dangerous overconfidence. Scientists assumed every gravitational anomaly could be solved identically. When Mercury exhibited similar orbital irregularities, astronomers immediately began searching for another hidden planet. They called it Vulcan. They searched for decades. It didn't exist. Mercury's anomaly would remain unexplained for nearly 60 years, a small crack in Newtonian physics' foundation that eventually revealed the entire framework required fundamental revision. Here's something that should deeply puzzle you. Gravity is spectacularly, almost absurdly weak compared to other fundamental forces. Consider electromagnetic force. A refrigerator magnet can lift a paperclip against the gravitational pull of the entire Earth. One tiny magnet overcoming the combined gravitational attraction of a planet containing 6 × 10 to the power of 24 kilograms of mass. Or consider static electricity. After shuffling across carpet, you can create a spark strong enough to feel. Yet 2 people standing 1 meter apart attract each other gravitationally with a force weighing less than a single bacterial cell. Quantitatively, gravity is approximately 10 to the power of 36 times weaker than electromagnetic force at subatomic scales. That's a 1 followed by 36 zeros, a difference so enormous that comprehending it becomes nearly impossible. This weakness creates a paradox. If gravity is so feeble, why does it dominate cosmic scale phenomena? Why do planets orbit stars? Why do galaxies hold together? Why does gravity, not electromagnetism, determine the universe's large-scale structure? The answer lies in several critical properties. First, gravity's weakness decreases with distance, according to an inverse square law. Double the distance, and gravitational attraction drops to 1/4. Triple the distance, and it falls to 1/9. This rapid fall-off with distance applies to all forces following inverse square laws. But gravity possesses 2 unique characteristics. First, it only attracts, never repels. Electromagnetic forces can push or pull depending on charge. Positive repels positive, negative repels negative. Opposite charges attract. This means electromagnetic forces frequently cancel out. Most matter contains equal quantities of positive and negative charges, rendering it electrically neutral. Gravity has no negative mass. Mass only attracts mass. Always. No cancellation, no neutralization. Pure accumulation. If this is blowing your mind, hit that like button and subscribe. We're just getting started, and it gets way stranger from here. Second, gravity acts on everything. Electromagnetic forces only affect charged particles. Nuclear forces only operate at subatomic distances. But gravity influences every particle with mass or energy, which means everything. So while individual atoms barely attract each other gravitationally, collecting 10 to the power of 50 atoms into a planetary mass object means 10 to the power of 50 tiny attractions summing together. No cancellation, pure addition. The cumulative effect becomes overwhelming. This is why gravity shapes the cosmos despite its intrinsic weakness. Stars form when gravitational attraction pulls together vast clouds of hydrogen gas spanning light years. The sun contains approximately 2 times 10 to the power of 30 kilograms, 2 million trillion kilograms. At that mass scale, gravity dominates everything, initiating nuclear fusion in the core and maintaining hydrostatic equilibrium for billions of years. Galaxies contain hundreds of billions of stars plus vast quantities of dark matter. Their combined gravitational fields are so powerful they bind these stellar systems together across distances measuring tens of thousands of light years. Galaxy clusters, the universe's largest gravitationally bound structures, can contain thousands of galaxies with total masses exceeding 10 to the power of 15 solar masses. Their gravity is so intense, it visibly bends light from background galaxies, gravitational lensing that maps the distribution of invisible dark matter. Gravity is weak, but it's relentless. It never turns off. It never cancels. Given sufficient mass and time, it sculpts galaxies, bends space-time, and ultimately determines the universe's fate. The astronaut floating in cosmic imagery exists in a realm where gravity's apparent weakness has transformed into overwhelming strength. Mercury, the sun's nearest planetary neighbor, harbored a secret that would eventually demolish the Newtonian framework of gravity. Mercury orbits the sun in an ellipse, an elongated circle. This ellipse itself rotates gradually over time, a phenomenon called perihelion precession. Picture an oval orbit, slowly spinning like a hula hoop, rotating around its center. The point of Mercury's closest approach to the sun, the perihelion, shifts position with each orbit. Newtonian mechanics predicted this precession. Other planets' gravitational influences tug on Mercury, gradually rotating its orbital ellipse. Mathematicians calculated exactly how much precession these planetary perturbations should produce. Observations didn't match predictions. Mercury's perihelion was precessing approximately 43 arcseconds more per century than Newtonian equations predicted. To visualize this, an arcsecond is 1/3600th of a degree. 43 arcseconds per century means Mercury's orbital ellipse rotates about 1/84th of a degree more per century than predicted. Incredibly small, detecting a human hair's width from 10 meters away, yet measurable, undeniable, real. Drop a comment. Would you have ignored a discrepancy this small, or would you have suspected something fundamentally wrong? Scientists debated this for decades. Scientists desperately sought explanations. Perhaps an undiscovered planet orbited inside Mercury's path, gravitationally perturbing it. They named this hypothetical world Vulcan and conducted systematic searches, particularly during solar eclipses when the sun's glare wouldn't overwhelm observations of nearby space. No Vulcan. The planet didn't exist. Perhaps an asteroid belt inside Mercury's orbit caused the anomaly. Calculations demonstrated insufficient mass even if substantial material existed there. Maybe the sun wasn't perfectly spherical. Perhaps equatorial bulging created enough asymmetry to affect Mercury's orbit. Measurements showed the sun's shape couldn't account for the discrepancy. Perhaps Newton's inverse square law needed modification. Maybe gravity weakened slightly faster than 1r² at close distances. But any adjustment fixing Mercury's precession destroyed accurate predictions for every other planet. The modification had to be precisely calibrated for Mercury while leaving everything else unchanged, an obvious sign that something more fundamental was wrong. For nearly 60 years, Mercury's anomalous precession remained unsolved. Most scientists dismissed it. 43 arcseconds per century seemed too trivial to matter. Newton's laws worked brilliantly for everything else, predicting comet returns, explaining satellite motions, enabling navigation. Why abandon 2 centuries of success over one tiny discrepancy in the innermost planet's orbit? But a few physicists recognized what this anomaly represented: a crack in the foundation, a whisper from the universe that something fundamental was wrong with humanity's gravitational understanding. The stubborn little anomaly was telling anyone who'd listen that gravity wasn't what Newton thought it was, that the mathematical framework, while predictively powerful, was incomplete. That reality operated on principles Newton's equations couldn't capture. In 1915, a German-born physicist working in Berlin published a radical new theory of gravity. Albert Einstein's general theory of relativity predicted Mercury's precession exactly. No hidden planet, no modified inverse square law, no adjustable parameters, just a completely different understanding of what gravity actually is. The answer was so strange, so counterintuitive, that even today most people struggle to accept it. Gravity isn't a force at all. Einstein's breakthrough was recognizing that gravity isn't a force pulling objects together. Instead, gravity is curvature in the 4-dimensional fabric of space-time itself. That probably sounds like meaningless jargon. Curvature of space-time. What does that actually mean? Let's build understanding step by step, starting with concepts you already grasp. Consider space and time as we normally conceive them. Space is the 3-dimensional arena where objects exist and events occur. You can move forward, backward, left, right, up, down. Those are space's 3 dimensions. Time seems fundamentally different. It flows unidirectionally from past to future. You experience events sequentially. You cannot reverse time's arrow or arbitrarily jump forward. Space appears to be where things happen. Time appears to be when they happen. Completely separate concepts. Einstein demonstrated this separation is illusory. Space and time aren't separate entities. They're woven together into a unified 4-dimensional structure called space-time. Not merely a mathematical abstraction, a description of physical reality's actual structure. You cannot have space without time, or time without space. They're different aspects of the same underlying entity. When you move through space, you simultaneously move through time. When time passes, you're traveling through space-time, even while remaining spatially stationary. Every event in the universe occurs at a specific space-time location, not just where and when separately, but at a definite position in 4-dimensional space-time. Hit that subscribe button if you're following along, because what comes next about curved space-time is going to completely transform how you see reality. Here's the crucial insight. Space-time isn't rigid. It's flexible. It can bend, warp, and curve. What causes curvature? Mass and energy. Every object possessing mass or energy curves the space-time surrounding it. Greater mass means more curvature. Earth curves space-time around it. The sun curves space-time far more dramatically because it's vastly more massive. Even you curve space-time minutely, an imperceptibly tiny amount, but real nonetheless. This is gravity, not a force transmitted across empty space, but the geometric curvature of space-time itself. Think of a trampoline stretched taut. Place a bowling ball on it, creating a depression. Roll a marble near the bowling ball, and the marble doesn't travel straight. It curves toward the bowling ball, following the trampoline's sloped surface. From the marble's perspective, it's following the straightest available path. But because the surface is curved, that path bends toward the bowling ball. This analogy has limitations we must acknowledge. The trampoline is a 2-dimensional surface curving into a 3rd dimension. But space-time is four-dimensional and isn't curving into some higher dimension. The curvature is intrinsic, a property of space-time itself, not bending into external space. Also, the trampoline analogy uses gravity to make the bowling ball sink, creating circular reasoning when explaining gravity. So treat it as visualization aid, not literal description. Similarly, Earth curves space-time around it. When you drop a ball, it isn't pulled by a force. It follows the straightest possible path through curved space-time. That path happens to curve toward Earth's center because Earth's mass warps space-time geometry. The straightest possible path through curved space-time is called a geodesic. In flat space, straight lines represent shortest distances between points. But in curved space, traditional straight lines don't exist. Instead, geodesics represent shortest paths through that curved geometry. Objects in free fall follow geodesics. Planets orbiting stars follow geodesics. Light beams follow geodesics. Everything follows the curved contours of space-time. On Earth's curved surface, the shortest path between distant cities isn't a straight line through the air. It's a curve following what's called a Great Circle route. Flights from Los Angeles to Dubai fly over the Arctic. On a flat map, this looks absurdly indirect. On a globe, it's actually the shortest route. In curved space-time, objects follow geodesics. A planet orbiting the sun isn't pulled by a force. It's following a geodesic through space-time curved by the sun's enormous mass. From the planet's reference frame, it's moving straight ahead. But because space-time is curved, that straight-line motion from our external perspective looks like an orbit. The planet continuously falls toward the sun while simultaneously moving sideways, fast enough to keep missing it, a perpetual state of freefall. This explains astronaut weightlessness in orbit around Earth. They're not beyond Earth's gravitational influence. At the International Space Station's altitude, approximately 400 kilometers, gravitational field strength remains about 88% of surface value. Astronauts feel weightless not because gravity disappeared, but because they're in free fall, following a geodesic through curved space-time. The space station and everything inside it follows the same geodesic simultaneously. Relative to each other, everything floats. This leads to Einstein's equivalence principle, one of general relativity's foundational concepts. Picture yourself in an elevator. The cable snaps. Terrible scenario, but bear with me. As the elevator plummets, you'd float inside it. You wouldn't feel weight. You'd be in free fall along with the elevator. Now imagine you're in deep space, far from any star or planet. You and the elevator drift. You'd also float because nothing pushes against you. Comment below. Does this thought experiment help you understand Einstein's insight? Let me know what clicked for you or what still seems confusing. Einstein's insight. These situations are equivalent. Free fall in a gravitational field and floating in deep space with no gravity create identical experiences. You cannot distinguish them from inside the elevator. This is the equivalence principle, the foundation of general relativity. Similarly, consider standing in an elevator on Earth. You feel the floor pushing upward on your feet. That's weight. The floor resisting your tendency to follow a geodesic through curved space-time toward Earth's center. Now imagine a rocket in deep space accelerating at 9.8 meters per second squared, identical to Earth's surface gravity. You'd feel the rocket floor pushing up on your feet exactly as on Earth. From inside the rocket, no experiment could distinguish whether you're standing on Earth or accelerating through deep space. These situations are equivalent. When you jump, you experience momentary freefall. That brief airborne moment, you're weightless. You don't feel weight pressing on your feet. The moment is so brief you barely notice. But if you could extend it, remove the ground so you continued falling, you'd feel exactly what astronauts experience in orbit. True weightlessness. The equivalence principle leads to strange predictions. One is gravitational time dilation. Time passes at different rates depending on position in a gravitational field. Stronger gravitational fields mean slower time passage. Not perception, not subjective feeling, time actually passes at different rates in different locations. This seems impossible. Time is time, right? A second is a second everywhere. Wrong. Time is variable. If you're standing on a massive planet's surface where space-time is highly curved, time passes more slowly for you than for someone in orbit where space-time is less curved. Take two synchronized atomic clocks, the most precise timekeeping devices ever built. Place one on the surface and one in orbit. When reunited, they'd show different times. The surface clock would show less elapsed time. This has been measured experimentally countless times with stunning precision. In 1971, scientists placed ultra-precise atomic clocks aboard commercial aircraft and flew them around the world. When landed, those clocks ran ahead of identical clocks, remaining on the ground by exactly the amount general relativity predicted. The difference was minuscule, measured in nanoseconds, but real and measurable. GPS satellites orbiting Earth must account for time dilation, or position calculations would accumulate kilometer-scale errors within hours. Atomic clocks on GPS satellites run slightly faster than surface clocks because they're higher up where space-time is less curved. The GPS system automatically corrects for this. Every navigation calculation on your phone relies on Einstein's predictions being accurate. If you're realizing that Einstein's crazy theory affects your daily life, smash that like button. Science is everywhere, and we're about to get even wilder. Think about this means. Time itself isn't constant. It's not an unchanging river flowing identically everywhere. Time is flexible, variable, dependent on gravity's strength. Near a neutron star, an object so dense that a teaspoon of its material would weigh 1 billion tons, time passes approximately 70% as fast as it does in deep space, far from gravitational sources. Near a black hole's event horizon, time dilation becomes infinite. Time effectively stops from an external observer's perspective, though someone falling inward experiences nothing unusual at the boundary itself. General relativity also predicts gravitational lensing. Light follows geodesics through curved spacetime like everything else. If light passes near a massive object, its path curves. Massive objects can act like lenses, bending light passing near them. First observed in 1919 during a total solar eclipse, astronomers photographed stars near the sun when solar glare didn't overwhelm starlight. They found stars appeared slightly displaced from known positions. The sun's gravity bent starlight passing near it. Displacement amount matched Einstein's predictions precisely. This findings made Einstein world famous overnight. Newspapers worldwide proclaimed the confirmation of his revolutionary theory. Today, gravitational lensing is standard astronomical practice, helping us map dark matter distribution and observe the universe's most distant galaxies. When light from a distant galaxy passes near a massive galaxy cluster between us and that distant galaxy, the light bends. Sometimes light takes multiple paths around the massive object, and we see multiple images of the same distant galaxy. Sometimes the galaxy stretches into arcs or rings, Einstein ring. By studying these lensed images, astronomers map mass distribution in the lensing object, including dark matter that doesn't emit light but still curves spacetime through its gravitational influence. Einstein's general relativity revolutionized our understanding of gravity from a mysterious force into spacetime geometry. Mass and energy curve spacetime. Objects follow geodesics through that curvature. What we perceive as gravitational attraction is actually geometric curvature of four-dimensional spacetime. Simple concept, profound implications. Black holes represent the most extreme example of curved spacetime physics predicts. A black hole is a region where spacetime curvature becomes so severe that nothing, not even light, can escape. The boundary of no return is the event horizon. Cross it, and all possible paths through spacetime lead inward toward the center. No escape, not because something pulls you inward, but because spacetime itself curves so extremely that every geodesic points inward. The future direction in spacetime literally points toward the center. Black holes form when massive stars collapse at their lives' end. A star represents a balance between gravity trying to compress it inward and pressure from nuclear fusion pushing outward. As long as fusion continues in the core, outward pressure maintains equilibrium. Eventually, massive stars exhaust their fuel. Fusion stops. Outward pressure vanishes. Gravity wins. The star collapses. If the star is sufficiently massive, more than roughly 25 times the sun's mass, the collapse doesn't stop. The entire star compresses into an infinitely dense point called a singularity. Around that singularity lies the event horizon. The horizon's size depends on mass. For a black hole with the sun's mass, the event horizon would measure approximately 3 kilometers in radius. This is called the Schwarzschild radius after Karl Schwarzschild, who calculated it in 1916, just months after Einstein published general relativity. For a black hole with 10 solar masses, the radius would be roughly 30 kilometers. For a supermassive black hole with 1 billion solar masses, like those at galaxy centers, the radius would be nearly 3 billion kilometers larger than Saturn's orbit. Share this video if black holes fascinate you. Hit subscribe and turn on notifications because we're exploring the weirdest objects in the universe. From a person falling into a black hole's perspective, they cross the event horizon in finite time, seconds, minutes, or hours, depending on the black hole's mass. From an external observer's perspective, watching, the falling person never quite reaches the event horizon. As they approach, time dilation becomes increasingly extreme. Time passes slower and slower for the falling person relative to the external observer. Light from the falling person becomes progressively redshifted, visible light shifting to infrared. Then radio waves becoming dimmer and dimmer. Eventually, the person appears to freeze just outside the event horizon, fading from view. But this is merely a perspective effect. The falling person experiences themselves falling through normally. Inside the event horizon, space-time warps so severely that the future points toward the center. Just as surely as your future in normal space-time points forward in time, your future inside a black hole points toward the singularity. You cannot avoid hitting the singularity any more than you can avoid moving forward in time outside a black hole. The singularity isn't a location in space you might avoid by moving sideways. It's a moment in your future that you will inevitably reach. At the singularity, space-time curvature becomes infinite. Matter compresses to infinite density. Our current theories break down. General relativity predicts the singularity, but cannot describe what happens there, because the mathematics produces infinities, usually indicating the theory has reached its limits. Most physicists think quantum effects, which general relativity doesn't include, become important before reaching the true singularity. But we don't have a complete quantum gravity theory yet. We cannot say for certain what happens at a black hole's very center. That's the final terrifying truth about gravity. Strong enough, it doesn't just curve space, it curves your destiny itself. In September 2015, humanity detected something extraordinary. The Laser Interferometer Gravitational Wave Observatory LIGO picked up ripples in space-time itself. 2 black holes, 29 and 36 solar masses, had spiraled into each other 1.3 billion light years away. As they orbited, they emitted gravitational waves, ripples in space-time's fabric, traveling at light speed. Einstein predicted gravitational waves in 1916, but believed they'd be too weak to ever detect. For a century, they remained purely theoretical. LIGO proved him wrong. The facility consists of 2 detectors, one in Louisiana, one in Washington state, separated by 3,000 kilometers. Each has 2 4-kilometer-long arms arranged in an L shape. Laser beams bounce along these arms. When a gravitational wave passes through, it stretches space in one direction and compresses it in the perpendicular direction. The detected change was approximately 1/10,000th of a proton's diameter, like measuring the distance to the nearest star system to within a human hair's width. The precision required is almost incomprehensible. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events, mostly black hole mergers, but some neutron star collisions. These observations test general relativity in the most extreme conditions imaginable. Every detection confirms Einstein's century-old predictions. If this journey through gravity's true nature has changed how you see reality, please like this video Subscribe to the channel and share it with someone who needs their mind blown. Drop a comment telling me what surprised you most about gravity. Where is gravitational physics headed? Testing general relativity in even more extreme conditions. The Event Horizon Telescope continues observing black holes, searching for any deviations from predictions that might hint at new physics. Gravitational wave detectors are becoming more sensitive. LIGO is being upgraded. New detectors are under construction in Japan and India. The Laser Interferometer Space Antenna, LISA, is planned for the 2030 seconds, consisting of 3 spacecraft in a triangle with sides 5 million kilometers long. LISA will detect lower frequency gravitational waves from sources like supermassive black holes merging when galaxies collide. Another frontier is quantum gravity, unifying general relativity with quantum mechanics. Several experiments are being designed to probe the interface between these theories. This is incredibly challenging because quantum gravitational effects are expected to be significant only at the Planck scale, approximately 10 to the power of -35 meters, 20 orders of magnitude smaller than a proton. We cannot build particle accelerators reaching those energies. But there might be subtle effects we can measure indirectly. What should you take away from all this? First, gravity isn't a force pulling objects together. It's space-time curvature. Objects follow geodesics through curved space-time. When you feel weight, you're feeling electromagnetic forces preventing you from following your natural geodesic. Second, space and time are unified into space-time. Space-time is dynamic, curving in response to mass and energy. Third, general relativity has been confirmed by countless experiments, from Mercury's precession to gravitational wave detection to black hole imaging. Every test has supported Einstein's theory. Fourth, despite its success, general relativity is incomplete. It doesn't incorporate quantum mechanics. We need quantum gravity to fully understand the universe. Finally, understanding gravity means understanding that you live in a universe of curved space-time. You're not held to Earth by an invisible force. You're following the natural contours of 4-dimensional geometry. You're not being pulled down. You're following a geodesic through curved space-time. You're surfing the geometry of the cosmos itself.